Hi everybody, welcome to server-side prototype pollution, black box detection without the DOS. Detecting server-side prototype pollution legitimately is quite difficult because it often involves changing the state of the object prototypes on the server, and that can almost certainly lead to denial of service. I've created multiple techniques that will allow you to detect SSPP without bringing the server to its knees and without needing the source code. I absolutely love JavaScript. I'm obsessed with JavaScript. And I work at Portsmouth as a full-time researcher, and I consider it the best place to work there is. I enjoy researching new attack techniques, and I also like to do crazy things. So sometimes you get something in your head and you have to do it. That's what I'm like. For example, I created a browsable 3D world with just CSS, just for fun. I tried to sandbox JavaScript with regular expressions just because people said sandboxing HTML with regular expressions was hard, so I thought I'd give it a go with JavaScript. And then I've also written a book called JavaScript for Hackers that details my approach to JS hacking, fuzzing, browser hacking, DOM clobbering, and prototype pollution, all sorts. So first, I'll give a brief introduction to JavaScript prototypes and prototype pollution. Then I'll discuss why denial of service is a big problem. Then next, I shall cover the detection methods. I'll go through my first failed attempts that caused denial of service. Then I'll cover useful techniques that you can use as a manual tester to find prototype pollution. Then I'll cover automated detection methods that I've implemented into a scanner. After that, I'll share generic techniques for detecting prototype pollution, and then how you can use the Burp Collaborator or similar tools to detect prototype pollution asynchronously. I'll share a surprising discovery which resulted in a method to detect JavaScript engines and even leak JavaScript code. After that, I'm going to introduce an open source app that you can use in your own apps to detect prototype pollution. And we're also going to do some free Academy labs within the next few days where you can test this out. Then I'll show you what you can do to prevent prototype pollution, and then finish up with key takeaways and leave 5 minutes for questions. So I'm going to give you a brief introduction for prototypal inheritance and how prototype pollution occurs. So some of you might be already familiar with this, but it really helps if I explain this so that you can understand the basic concepts. So if we have an object and it's got two properties, A and B, and we modify the global object prototype and add a property C and give it a value of 3. So what happens now is the object itself inherits this property C from the global object prototype. Now what's interesting is the object itself mustn't have this C property in order for this inheritance to occur. And that's an important fact when trying to exploit prototype pollution. Almost all objects inherit from the global object prototype. The prototype chain is used to determine what properties the object should have. So here at the bottom, we have an object. So because it's an object type, it inherits from the object prototype, and it continues all the way to null, to the top prototype. Now, most people think that's where the prototype ends, but in actual fact, there's a special object. I think Chrome call it the global object polluter, and you used to be able to customize that, and I use that technique to hijack JSON. So, but in a modern browser now, you can't modify it. So once you get to null, the inheritance stops. So JSON.parse is a common cause of prototype pollution because it enables you to create an object that has a regular own proto key. In this example, we first create an object that's got one property, and we look at the proto, the special getter setter, and if we call has own property, so has own property will tell you if the property is inherited or not, or it's an own property, i.e. not inherited. And if we call that function, we can see that proto is in fact an inherited property, so own property is false. And then we use JSON.parse to parse a JSON string, and we assign it a proto key. But what's interesting now is when we use JSON.parse and we use the has own property method, Proto is actually an own property. It's not inherited. And this is one of the components of prototype pollution, because enumeration will be done on that property. So another component of prototype pollution is a recursive merge function. So in this instance, it's Lodash. So we're calling the merge function in Lodash, and it merges the object on the left, the user details object. It could be any sort of object, with the request body on the right, which comes from an attacker. So an attacker can modify the request body and it gets merged with the object on the left. And this is one of the components of prototype pollution, a merge operation. The recursive merge function enumerates all the properties of the source object and assigns them to the target object. I can't show you all of the code because it won't fit on the slide. However, the gist is the object gets enumerated, and it can result in prototype pollution if the keys aren't sanitized. So it will enumerate all the properties of the object. Because the proto property is an own object, that will work with enumeration. And this is why prototype pollution occurs, because you can use the proto key to change the object prototype. So you might be wondering what is possible with server-side prototype pollution. Well, you can change the application configuration or the behavior, which can result in RCE. Michael Benkowski and Paul Gerst both found RCE using prototype pollution in different applications. So when I started testing for prototype pollution, what became apparent was that denial of service was a big problem, but there is also a catch-22 situation when detecting prototype pollution. So you don't want to cause denial of service, but you need denial of service to know if the prototype pollution has worked. So you're stuck in this catch-22 situation where you don't want to cause denial of service, but denial of service can prevent the application from working, so it's not ideal. And it's the only way to test that prototype pollution has happened, or it seems anyway. So ideally what we need is some non-destructive techniques that change the behavior of the application subtly. So in this section, I'm going to show you my first failed attempts at detecting prototype pollution that actually caused denial of service. So I customized Node to help me find prototype pollution vulnerabilities, which I dubbed Node Invader. So you remember I said right at the top of the chain, you can modify the object in certain browsers, but not anymore because it's modern. I customized Node to allow me to do that, and that enabled me to find properties that access the object prototype. One of the first properties that I found was encoding, and this is a JSON request. I've trimmed it down so we can fit more stuff on the slide. But the idea here is you inject Proto with an encoding and you change the encoding property to X, and that just takes down the server. And the reason it takes down the server is because the node itself throws this exception. So if you're not catching this exception, then the whole process will shut down. And it's because encoding X is not a valid encoding. So X is not a valid encoding. So Node will throw an exception. And obviously this is no good for prototype pollution. So after many failed attempts, I decided to take a different approach. So this technique changes the methods on the object constructor. So when you've got like a function called object.keys and you call that method, it changes one of those methods. So before the probe, we've got some JSON and we get a 200 back. So we've just sent some valid JSON, get 200 back. And the probe alters the object constructor, modifies the key function. And what's interesting is this isn't actually prototype pollution because there's no prototypes involved. But what it does is it modifies the object.keys method with a string. And then whenever you make a JSON request, you get a 500 back. And yeah, obviously that detects prototype pollution, but you can't break every request on the application. So obviously it's not ideal. So after trying many different properties, I decided why not guess them. So I thought, okay, how about using the expect request header? So first I sent some JSON and get 200 back. And then I send a probe with the expect property with some arbitrary value, and then send the same probe again. And this time I get a 417 expectations status code. So, but the problem was that this expectation status code was appearing every time. Well, remember, I didn't have a clue where in the source code that this was happening, so I needed to investigate it and find out why. So one of the easiest ways of doing this is you use the -- inspect -brk flag in Node, and this will pause the Node process until you attach the debugger, and then you can use the debugger then to call console.trace whenever your target property is read. So in this case, if the expect property is read, you'll get a stack trace from Node. You can then investigate it by just clicking in Chrome DevTools and find out where exactly the code happens. And it appeared to be in the Node HTTP server code, and they were checking to see if the expect property was not undefined. And this is important because you can't produce an undefined value from a JSON parsed data. So there was no way to turn it off. So unfortunately, the expectation status code would always show, which is not ideal. So this wouldn't be a talk with me if XSS wasn't being involved somewhere along the way. And today's no exception. So before I send a request with some JSON and I get a JSON response back, then I send a probe that has the underscore body property set to true and the body property set to some script, some evil script. And what actually happens is when you make the request, Express will serve up that script as HTML and not JSON. So obviously this is stored XSS, and again, not suitable for prototype pollution. But yeah, it was fun to find. This happens when you use the res method from the response and you output the object. You can cause this to serve up HTML instead of JSON. So to recap, really, what we need to do is we need to find some valid vectors that don't take down the server or break the functionality. Ideally, what we want to do is find a technique that we can switch on and off, because that's a reliable way of detecting prototype pollution on the server without needing the source. So we've looked at vectors that can break the application or take down the server. Now we're going to look at vectors that can subtly change the behavior of the server. These vectors didn't make it into the scanner, but are really useful for manually testing for prototype pollution or combining them with other attacks such as cache poisoning. So this technique changes the maximum allowed parameters in Express. So before we send a probe, we have a parameter called X and a parameter called foo. And then we have a response that reflects that foo parameter back. So our probe then changes the parameter limit to 1. So this is just an example. You would probably use an upper limit so that you don't break the server functionality. So we change the parameter limit to 1 via prototype pollution. And then when we make the request again, the foo property is not reflected, so we don't have the value. So this proves you've got prototype pollution, and you can use it in a way that won't break the site or break it for other users. So this technique modifies Express to allow the question mark in a parameter name. So before we send the probe, we send 2 question marks, and then we look for a reflection, and foo is not reflected because it has 2 question marks. So the parameter name will actually be question mark foo. So when we inject the prototype pollution that changes the Express configuration, suddenly now we're allowed to use double question marks in the get request. So then when we send this probe, we get back foo and bar. Yeah, the double question mark is allowed, And you can use this with other attacks such as cache poisoning, because you can confuse the server to caching your evil request and not the legitimate request. So this technique allows you to change parameters into objects. So here we use foo.bar equals baz, and what we get back is foo is undefined. So the server is reflecting foo. So what we can do is inject prototype pollution with allow dots, and this will convert it into an object. So when we send the request again with foo.bar equals baz, we actually get an object back. So this can be used to verify you've got prototype pollution, and it can also be used in other attacks that require a specific object structure, and the Express server is not configured to allow objects in the query string. You can change that and use it in that way. So UTF-7 is a base 64-like character encoding that was used in the past to create encoded XSS vectors in legacy browsers such as IE. So before I send a probe, I send some. What this represents is UTF-7. So it's like base 64 encoded with a plus and a minus. So it's an encoded bar value. So when I get the response back from the server, it reflects it back as is because it's a UTF-8 character set and it won't be decoded. So then what we can do is inject our own content type. So via prototype pollution, we inject our own content type with the application/JSON content type and a UTF-7 character set. And what happens is really interesting, because now our UTF-7 encoded payload is then decoded, which results in bar being reflected. So this is a fantastic way of manually testing for prototype pollution, because it's not likely to be destructive. And what also is interesting is the response is served with the UTF-8 character set, but what is actually changed is the JSON itself. So the JSON itself uses UTF-7 character set. So I identified the line of code where this property was read. So what they were doing, they were parsing the JSON request, getting the parameters, getting the char set, or setting it to blank, and then that's what the code did to get the char set. But after writing this technique up and putting it on the blog, Andre, one of my colleagues, asked a very, very valid question. How come the original char set in the request content type header doesn't prevent prototype pollution? After all, I've just gone over that, where you can't have an existing property. You have to have a unique property that's inherited. So after we analyzed many lines of code and debugged a lot of JavaScript, what we noticed was the original content type in the request was being removed when you used the polluted content type property. And this was because in Node, they have this function called add header line. And on the red highlighted part of that, if you can see it, hopefully, if you can't see it, it basically says dest and then a property accessor with field. And if it equals undefined, then what it'll do is it'll add the header. So if it's not undefined, and it won't be undefined because we've polluted the prototype with the object prototype with the content type. So when Node checks to see if that field exists, it will exist because we've injected it, and therefore it won't have the original content type. And that's why it works. It was quite tricky to find that, but yeah, it was good fun. So I've talked about how you can manually test for prototype pollution. Now we're going to discuss some techniques that we can use for automation. These techniques subtly change the application behavior without causing denial of service. And that's the key, without denial of service. So this technique changes the padding of the JSON response. So if you send a probe with some JSON in the request body, and you get back some JSON and you observe the raw request, you'll notice there are no spaces in the response. But if we inject via prototype pollution, the JSON spaces property, so it's JSON spaces, and then assign a value to it, a space, 1 space, 2 spaces, whatever you like. Then when we send the original request again, the actual JSON response will have spaces. So this is a brilliant way of detecting prototype pollution, because spaces aren't going to cause any harm on the response normally, especially in JSON. It's not actually in the property names or values. It's on the outer part of it, which will just be ignored. So this is a cool way of detecting prototype pollution. Unfortunately, one of the devs of Express patched this on their own. It was fixed in 4.17.3, but it's still a cool technique that you can use on servers that don't upgrade the Express package. So I looked at other modules too, and I thought the cores module would be a good target, as it's commonly used for API endpoints. So any base request will do in this instance. We just need to observe the response, and then we send a probe that changes the exposed headers property in Express. So we add a foo property on the exposed headers response, and then when we send a request again, we actually get an access control exposed header response with our foo property. So that confirms that prototype pollution has happened, because that header will not exist normally when browsing the site. And it can be harmful to expose that header, but if you use like an arbitrary header, then it's pretty safe. So this technique uses the status code to determine if prototype pollution has worked. So I've included here, I don't know if you can see, it's pretty difficult from over there probably, but this is a JSON request with a comma. So it's an intentional comma that causes a bad request response code. So then we inject our probe that adds an arbitrary status. So in this case, I'm using 510 not extended status code. And then we do our probe again with some invalid JSON. And what we get back from the server is a 510 response code, which is ideal, which is perfect, because that proves that the prototype pollution has happened. And we can reset this too. So if you do the probe again with 0, that will turn off this and allow you to use the site as normal. So first this one uses the options method. So first we send an options request. So here we send an options request and we get back some methods. So we get the post, get, and head method back. And then our probe here sends the property of head equals true. So when this happens, the response code, the request method will skip the head method, and the response will just show post and get. So you can use this method to determine if prototype pollution is successful, and then switch it off to resume. So this technique uses a property reflection to determine if prototype pollution is likely. So this is not it doesn't prove that prototype pollution has happened, but it proves that it likely could happen. So first we send a proto key with a canary in there, and we get a response back. So when we send a probe with proto X and that is reflected, that's an indication that proto is behaving differently. And that's interesting for prototype pollution, and the tool will flag that because it's worthy of investigation. And if you send a probe without any property in there, and if you get your proto property back, so if you get the canary back, then it's a really good indication that there's prototype pollution, or you've got some sort of object persistence. I've cut the code down here, but the idea is you have an inherited property and a regular property, and if one of them is reflected, it's still interesting because you've either got object persistence or you've got prototype pollution. And this is one of my favorite techniques. So here we send some prototype pollution. This one was found in the Lodash library, but it is a generic technique that can likely be applied to other libraries. And how it works is you send an inherited property. So in this case, it's A. So we inject an inherited property A and then a regular property A and B. And if the server reflects the object back and B is reflected, but A is not, this is a strong indicator of prototype pollution. And this is because Lodash loops through, there's like an assign merge value function, and it loops through the object and it uses the in operator. The inner operator is quite important because it checks for inherited properties. So what Lodash is doing is trying to return this merged object, but before it returns all the properties, it uses the in operator to see if that property already exists. And it will exist because there is an inherited property called A, and that's why it's skipped. And this is a generic technique that can be applied to pretty much any library that is a very good, strong indicator of prototype pollution. So Paul Gerst blogged about exploiting prototype pollution, exploiting a prototype pollution vulnerability in the Super JSON library, which resulted in RCE and Blitz. I definitely recommend you check that out if you can, because it's really cool. So Blitz uses a library called Super JSON, and it allows you to reference different parts of the JSON structure using arrays. Now, I spent a lot of time on this slide to help people understand because I didn't get it at first. Hopefully I've arranged it in a way that is easy to understand. I've used colors to indicate what's being modified. But the idea is here, brands.0 gets the brands object, which is in green, and then the value from the array is then transferring that brands object into the value specified in the array. So here it's products.0.brand. So the brand object is being moved or copied into that value in the JSON. This is how you can get prototype pollution, because if you can control multiple properties, then you can use proto.targetKey, for example. So in this example, we get the brand name and we assign the value to proto.targetKey. So this is how prototype pollution works in the Super JSON library. So what's interesting though is what if, do you remember I talked about this super global polluter? So if you try and assign that to an object in Chrome or any other browser, any other JavaScript, what you get back is that this is immutable. You cannot change that prototype. And we can use that difference to determine if you've got prototype pollution for any library that allows you to assign multiple properties in this way. So you'll get a proto.proto will be the global object polluter. You'll get an internal server error which will say immutable prototype object cannot have the prototype set. So to summarize, when you assign to proto.proto using an object literal, it will throw a type error exception, whereas a primitive string such as string or null will not. So this offers a generic way to detect Blitz style Super JSON prototype pollution. If you try and assign that value with a string, no type error. If you try to use an object, you'll get a type error. So we can use that difference to detect prototype pollution. In this section, I'm going to show you how to detect prototype pollution asynchronously using Burp Collaborator or similar tools. So here are some syncs in Node that are vulnerable to prototype pollution. Note that in order to exploit any of these syncs, you do not need control over the arguments. So as long as you're executing a command, it doesn't matter. You can control what is executed via prototype pollution. A paper by, and this is a tough one to pronounce, so I'll try, Mikhail Sherbakov and everyone else, there's a few people who did this research, demonstrates how to exploit the syncs on the previous slide using node options. So node options allows you to pass command line options to the node process. It's a brilliant paper, absolutely fantastic research. You should check it out. So yeah, how can we scan for these vulnerabilities though? Well, no, I spent some time trying to come up with detection techniques that would find usage of those sinks. The problem is Node blocks the command line argument -- eval in Node options. However, you can use -- inspect, which allows you to specify a host for a remote debugging session. So this creates a DNS interaction, which is perfect for scanning. And as a bonus, if you can control the -- inspect flag, you can get remote code execution because you can connect to a remote debugging session and execute your code. So this optimized payload should detect the sinks using the -- inspect command line argument. So here what's important here is the shell command. So when one of those functions gets called, it has a shell property that if it isn't present, you can then choose the shell to execute. So in this case, we execute node, we pass the node options with -- inspect. That will create a DNS interaction, and that will prove the function has been controlled with the node options inspect flag. The problem is you're going to get some false positives. And the reason you get false positives is that some sites will scrape the host. So the solution to that is just obfuscate the host. So I started to look into this. I tried all sorts of ways of obfuscating the host, including single quotes, dollar curly braces, etc., lots and lots of different ways. And then I discovered that you can just use double quotes, and that works on every OS, Mac, Linux, and Windows. So this will be ignored on each OS. So you can obfuscate the URL being used, and using the double quotes, it will be ignored, and the scraper will not be able to parse that URL. And if you get a DNS interaction, then you should have remote code execution, really. So whilst conducting this research, I found it was possible to detect a JavaScript engine being used and even leak JavaScript native code using certain parameters. So I asked myself the following question. What would happen if you used inherited properties in a parameter name or value, or even a cookie value or a cookie name? Could I determine the JavaScript engine? Maybe. What if I modified the prototype pollution scanner to look for these properties, and to my surprise, I found multiple sites leaking JavaScript native code. Here we make a request to creative.adobe.com with a cookie called cookie cloud lock and a value of constructor. Can we guess what's going to happen? We get JavaScript native code. So what they're doing is they're using that value as a property name, and it's proven because you're getting JavaScript native code being reflected back in the set cookie header. So constructor will work, value of will work, any sort of inherited property will work. So I went to see if more sites were reflecting objects in this way or behaving differently. And what I found was that you can use an inherited property such as value of as a get parameter. And what happens with Apple, for example, I think they've taken this site down, but the value of property will return an internal server error. But if you follow up with value of X, it won't. But if you use an inherited property like toString, for example, you'll get an internal server error. So the prototype pollution scanner will look for this behavior because it's super interesting, because the server is responding to properties like toString, inherited properties, and value of. So it's worthy investigation for prototype pollution. So it will give you a good indication where to look for prototype pollution. So by using this behavior, you can discover the JavaScript engine being used. So for example, if you're using Rhino, they have properties like toSource, iterator. So we can detect Rhino, and looking for specific inherited properties in a JavaScript engine can help detect it. So if any JavaScript engine uses some obscure property, you can use that with that behavior and scan for it and find all sorts that, as long as you know the properties that cause this behavior. It might work with other languages. I've not really tried, but maybe with Python and Ruby or something, but I've not really looked for that. So if a property like toSource doesn't exist, but lookup setter does, or there are other inherited properties like that, then it's probably V8, or it could be Rhino, or another engine that uses other specific properties, and you could search for those. So today I'm releasing an open source tool called the server-side prototype pollution scanner that will help you detect prototype pollution using the techniques mentioned in this talk. So it will scan for the automated scan checks that I demonstrated. It will scan for JavaScript inherited properties. It'll scan for the asynchronous stuff as well. So you get burp collaborator callbacks if the prototype pollution has worked. So you can use it to discover interesting behavior like I've demonstrated. We've also designed some free Academy labs too, so they are free. They're going to be released within the next few days, I think. So the scanner is open source. It will work on both Burp Suite Pro and Community Edition. It's available on GitHub. Probably after this talk, I'll change the privacy view to public. So it won't work right now, but it will. The Academy Labs will be available on here. There's also a white paper that goes into depth in the source code of the various prototype pollution attacks. So you can get the white paper on the Portswigger research blog. So I'd like to finish off discussing on how to prevent prototype pollution. So probably the best way is not to use object literals at all to define options functionality in your app. If you use set or map instead of objects, you can safely use them without being vulnerable to prototype pollution. Set is used when you have a list of values to check, or map is used when you have a key value per combination. If you cannot use map or set, then you can use the object.create API with a null prototype. So you just call the object.create API with a null value, and that will create a non-inherited object that doesn't inherit from the object prototype. If you must use an object literal, then as a last resort, you can use the proto property with a null assignment, and that will ensure that that object does not inherit from the object prototype, which means it's not vulnerable to prototype pollution. Node also offers a command line flag to disable or delete the proto property, which is really useful. It's called disable-proto, and you do =delete. This won't prevent prototype pollution because you can still get it with constructor.prototype. However, it's a good defense in depth measure if you're running a Node application, because hopefully there's no applications out. Hopefully there's no packages on your application that uses the proto property. And if there isn't, then you can just use this command line flag to disable it. Thanks for listening to my talk. The 3 takeaways from my presentation are: try and use the prototype pollution scanner. It'll hopefully find prototype pollution in your apps or interesting JavaScript behavior. Safe black box scanning is possible, and I recommend you use set or map instead of objects when defining object-like behavior or accepting a list of values. You can follow me on Twitter at Gareth Hayes and get the server-side prototype pollution scanner source code from GitHub on that URL. Thank you. Any questions? Sure.
Yeah, I'll get that.
Hello. So if I have full control over my code and I want to freeze the prototype, would that be enough for protection?
Yeah, you could use the object.freeze or seal methods. Yeah.
And it will cover me on all sides?
Not on everything, because
Like from your experience.
well, it depends what you freeze and seal. If you freeze like the object and the object prototype, then you should be all right. Yeah. What I was thinking was, if you're using like object dot keys, for example, and you just froze the prototype, then that wouldn't prevent that from happening, like I've demonstrated in the talk. But if you froze that as well, then yeah, you should be all right.
Amazing. Thank you.
No worries.
Any more questions?
Cool.
No? No more questions? So all I'm left to, thank you for such a great talk.
Cool.
And I'll request all of you to please give him a round of applause, please.